morning. We begin with lecture number 16. A quick recap of the key points from lecture number 15. The main concepts that we have covered is to introduce the multipath environment with the assumption of there is no line of sight path. So all of them are through some process of either reflection or diffraction. And we have looked at the model, the basic assumptions, and showed how the Rayleigh PDF emerges as the resultant envelope of the signal. So again, we will reinforce this through several examples and also through the derivations that we will be covering in the lectures. The goal of today is to look at some examples, some applications of and the consequences of the envelope of the signal becoming a Rayleigh distributed random variable. So once the envelope gets affected, the bit error rate performance also will get affected. Today's class we will touch upon that. There is a very classic example that is often discussed in the context of multipath channels that is found in the book by Say and Vishwanath. TNV is my short form for Say and Vishwanath, and I've indicated that that you should have a look at chapter 2, especially the beginning part of chapter 2, which will give us a good introduction, a very, very elegant example which helps us understand. The rest of the material, the main contents can be found in Molish chapter 5 and Rappaport chapter 5, basically the chapter in Rappaport which covers small scale fading. Again, there are some chapter number differences between the different editions, the chapter that contains small scale fading. Okay, so we begin today's lecture with a quick review of the material covered in the last class, and again if there are any doubts or questions, please do not hesitate to ask. So the multipath propagation model, no line of sight. So basically we assume that there is some building here which has affected even this path. So giving us a line of non-line of sight, 3 components in this case. We said that if S of t is the modulated signal, then we can write down these multiple arriving paths as a superposition of scaled by alpha n. That's a gain of each of the multipath components with the appropriate delays. If we take the form of complex baseband notation, S of t can be written in this form. Applying this to the multipath environment, we came up with the following expression that the received signal, this is complex baseband. Complex baseband notation says the received signal is a superposition of the complex baseband signal that was transmitted with different gains and delays, and that is represented by the time varying multipath channel. And if we want to think of it in terms of discrete occurrences of these multipath components, you can think of it as alpha n, which is a function of t and tau, the delays, the delay at which it occurs, and the corresponding phases, which will also be a function of t and tau. One of the very useful ways of visualization of a multipath channel is to think of it in terms of 2 dimensions. One dimension being the delay dimension, the other one being the time dimension. So at any given point, if you take a snapshot, you get a certain multipath profile. Basically number of multipath components, the delays, the gains that are occurring. We have shown a few examples. Now basically this is a visualization of what is in reality a continuous function. So it is continuous, the multipath profile is continuous in t, it is continuous in tau. Both are continuous. So basically it is the best way to visualize this, this channel response is as a 2-dimensional random process. It has some variations along the tau dimension which are dependent on the environment. There is some variations in the function of, along the time dimension which also depends on the position. So it's a 2-dimensional random process is a good way to visualize this, this channel response. It is random both in the time dimension as well as in the tau dimension. Now, if you take a particular realization of a random process, you get a random variable. So in this case, what is the random variable? If I specify t equal to t1 and I specify tau equal to tau 1. So which means at time t1 along this axis, along the tau equal to tau 1, this becomes a random variable. So particular sample or a particular realization becomes the sample function. So yesterday we said that if all of the multipath were arriving at the same time, then we could represent the entire channel response by means of a single complex term. But even otherwise, each of these can be visualized as random variables which can have a PDF, and again, as long as the basic assumptions are the same, that you have a large number of multipath components which are coming from different directions, together they are comprising this particular component, then you can say that each of these random variables also behave as Rayleigh distributed random variables. So the notion is that if I look at a specific time instant t equal to t1 and a specific delay tau equal to tau 1, a sampling of the random process gives me a random variable. This is what I will refer to as Z1. The modulus of Z1 is what has the Rayleigh PDF. So we have also used the notation that alpha, which is the amplitude of the random variable. You can say that alpha also has the same Rayleigh PDF. So is there visualization of as a two-dimensional process, a particular sampling point becoming a random variable, and thereby giving you a PDF that you can then interpret and apply in terms of our understanding of the multipath channel. Is that part clear? If there are any questions, I can clarify them. Otherwise, we move forward into building upon this basic assumption. Okay, we move on to understanding of this. Again, this is a repetition from last class, but for the specific purpose that we are trying to highlight, where does small scale fading come into the picture? Small scale fading comes over and above the large scale effects. The large scale effects being the path loss and the shadowing loss. These are the large scale effects. So the large scale effects gives me the the thick dashed line, and then on top of that, any movement within a 10 lambda to 20 lambda space gives further fluctuations. So basically, over and above the large scale variations, you will see small scale variations. So now again, so that in our minds we are very clear that this is not a different one, doesn't occur independent of the others. They all kind of act together. You have path loss, you have shadowing, you also have on top of that large scale fading. Okay, so again, the entire picture gives us a good understanding of the environment that we are working with. So the path loss, we all can assume, we understand, okay, the further away from the base station I move, I'm going to have a degradation in my signal. That is very intuitive. Shadowing also may be somewhat intuitive because you have an obstruction between you and the transmitter. So therefore, that also is reasonable to expect. The fast fading or the small scale effects are not intuitive until you have a good handle on what is happening, the process that is happening inside, and that is where the lecture that what we're covering yesterday and today is going to help us in our understanding. Okay, so let me go back to another important element which helps reinforce our understanding of the environment, the fading environment that we are working with. Now, in an AWGN environment, supposing you are looking at that, which is the computer assignment number 1 that you did, you have the modulated signal, baseband signal, and then on top of which you add the Gaussian noise. So, in other words, if I were to implement this in a block diagram, you would have the modulation followed by pulse shaping, and then you would pass it into the channel where noise would get added, AWGN would get added, AWGN, wide spectrum, but then when it passes through the receive filter, you reject whatever is outside of your band of interest. So you have the desired signal as well as the impairment that falls within your receive bandwidth. That is what passes through the receive filter, and that is what we receive at the demod. And this is what you have characterized in your simulation as BER versus EB over N0. And very familiar graphs. These graphs are quite steep. If you look at the performance, the BER performance drops very fast. This is EB by N naught, this is BER, and you have been able to generate these graphs. Now, what changes when you move from an AWGN environment to a multipath fading environment? So this is a multipath fading environment. Notice I am not calling it Rayleigh fading for a very specific reason, because we have made an assumption that there is no line of sight component. It is Rayleigh fading if there is no line of sight component, but multipath very much present, fading very much present. Whether line of sight is present or not decides it. If there is no line of sight, it will become Rayleigh fading. But in a multipath fading environment, let us say that this is the environment. So we said that the net of all the multipath components adding together gives me a random variable z of t. Z of t magnitude squared is what is going to affect, because mod z is what affects my amplitude, mod z squared is what is going to affect my SNR. So yes, in the yesterday's class we said that the resultant SNR in a fading environment is going to be mod z squared times the SNR that you would see in an AWGN environment. Okay. So now if I want to introduce this the fading into this process, then what I would have to do is introduce the fading, and let me just bring in the fading part. So where does fading occurs in the channel? Where does noise get added? In your receiver. So which happens first? Fading happens first. So fading happens first. Now what is the process of the impairment of fading? It comes as z of t multiplying u of t. So z of t, we make an immediate note, it is not an additive, impairment, it is a multiplicative impairment. And it happens before the AWGN comes into play. So again, it's very important that you we keep in mind the sequence, because this is where z of t is happening in the channel. Basically z of t gets multiplied. So all this says is when it comes to my receive side, even before the AWGN gets added, what has happened? My signal is going up and down, and there is a possibility that the signal has gone down. Now does AWGN care whether your signal is high or low? No, it just adds a certain noise level to the signal. So if it so happens that your signal has become faded and your noise, as always, the difference between these two actually keeps fluctuating, and that is what is represented by a SNR, which is not constant anymore, it is a time varying SNR. Okay. So that's a very, very important element. We'll come back to discussing this a little bit more towards the end of the lecture. But is this part clear, that we have introduced an impairment which potentially could have a very significant impact on my bit error rate performance, because the z of t is a fluctuating one. And we showed that there are some points where the Rayleigh fading can go quite deep, which means that your SNR can momentarily go very low. So which means that there is a impact on BR. How much of an impact? How do we overcome that? All of that is what we are going to study in the course. But is this basic notion of what happens when we move from an AWGN environment to a fading environment, is that reasonably intuitive and comfortable to everyone? Any questions? Okay. Now we move on to the second aspect of it. How do we understand this through computer simulation? So yesterday's class we talked about the scenario when two waves mix. And a very good question was asked towards the end of the lecture: how many such waves have to mix to get a Gaussian distribution of the real part and the imaginary part? So we will do a simple computer experiment which will show that even with as little as 4 waves, you start to see the Gaussian behavior. With 8 components, random components, you will see very good Gaussian distribution of the real part and the imaginary part. So basically, this is what will look like at the resultant at the end of after you do the simulation. So this is your position of the receive antenna. If it happens to be on a peak, you get good signal, you move slightly, dip little further, again there's a peak. So basically this is a spatial distribution. in the x and y direction. So in the plane, it is no longer a constant level. There is a variation in the signal level that is received. Again, through the computer experiment, we will reinforce this concept. Okay, so quickly let me summarize the key properties of the Rayleigh PDF. Again, keeping in mind that there are people who are probably seeing this for the first time, but more importantly, we just want to make sure that the basic assumptions are clear and that we are able to have a good understanding of what the impacts will be. So one of the key points that I want to mention is that there are three effects that we are looking at. One is path loss, there is shadowing, and then the third one is where we bring in the effects of fading. Okay, the small scale effects. So basically the third component is what we are looking at. And it starts off with by making the assumption of a superposition of a large number of random phasors. So there is a superposition that is happening, superposition of a large number of random phases, of n random phasors. That's an important part of our assumption. So basically the channel Z of t, we said can be approximated as n equal to 1 through n. We are basically making the assumption that all the multipath components are arriving at the same time. Alpha n of t e power j phi t comma tau, all of them have got the same delay, so tau is, so this can be written as summation over n equal to 1 to n of components, once we resolve them, as xn plus jyn. And each of these, this contributes two parts. One of them contributes the ZR part, the other one contributes the ZI part, the summation of those terms, and those are what give us the Gaussian distribution. So based on that, we then did a transformation of variables and showed that the envelope where v is equal to square root of x squared plus y squared, where x and y represent the Gaussian IID random variables, that's what was the distribution. So quickly, the properties that we have already derived in the last class, expected value of the random variable v, expected value of the envelope. Now you may wonder, any PDF has got mean, variance, what is the reason to actually spend time on looking at those values? One of the things that I want you to observe is the shape of the PDF. Are large values more likely or are small values more likely? So if you were to look at the sketch of the Rayleigh PDF, the Rayleigh PDF looks like this. So that tells you that Rayleigh PDF, the distribution of the envelope, this is the envelope, this is the probability distribution of the PDF, it is more biased towards small values. Now, or the smaller values are more likely to happen. The larger ones are part of a tail, which is very small. So what does that tell me? My envelope is going to affect my SNR. So therefore, I need to be very careful with Rayleigh PDF because it is going to shift my SNR to possibly to some lower values when fading is present. Okay. Now, in addition to that, another point to keep in mind, why is that an important element? Go back and just quickly look at your BER graph. Your BER graph is a very steep graph. So let us say that you had some value as you have defined as your EB by N naught, and you are very happy with the BER that you have gotten. Now suddenly if I multiply it with mod Z squared, and it happens to be a value that shifts it by 3 dB. 3 dB. What happens to your BER? All of a sudden, that what was considered as a good BER suddenly got perturbed to a very bad BER, because these BER graphs are very steep. If you shift by 3 dB, very easy to happen in fading, but the BER impact is going to be totally unacceptable to you. So this is why we are very interested in the mean, the variance, all of these are things. Otherwise, we wouldn't care too much about, okay, like every distribution has got a mean and a variance and all of that, but we are focusing more on that. So expected value of the distribution, yesterday we derived it, sigma times root pi by 2 also 1.253 sigma. Again, the values may give some insight. Expected value of V squared is 2 sigma squared. Okay. So, again, if I wanted the RMS value, I would take the square root of this, so it will be root 2 sigma. So, the RMS, so we can call it as V RMS will be equal to root 2 times sigma. Okay. That would be the root mean squared value. Now, the variance, not sure if we wrote it down yesterday, sigma V squared. Notice you have to be very careful not to confuse this sigma with the sigma of the Gaussian random variables. Each of these Gaussian random variables has got a variance sigma squared. This is different. This is the sigma squared of the envelope, the variance of the envelope. So, again, keep that picture in mind. Basically, this would be equal to expected value of V squared minus expected value of V the whole square. Basically, the mean squared value minus the square of the mean, that will give us a expression which will be sigma squared 2 minus pi by 2, which is 0.43 sigma squared. Okay. And or if I were to look at the sigma V, that would be 0.656 into sigma. Again, please make sure that there is a clear understanding of which belongs to the Gaussian, which belongs to the Rayleigh random variable, and keep those things in mind. So, the variance of the Rayleigh random variable is less than the variance of the Gaussian that we are dealing with. If you had a chance to look at the assignment that was uploaded just as called as assignment 3B, asked you to do some simple calculations. So, to look at the sketch of the PDF, plot that. Again, that's fairly easy for us to plot if you take V by sigma as a parameter, because then you can plot that, and on this graph we can then look at where the different points lie. So, one of the points that we are asked to check is where does the peak of the PDF of the Rayleigh PDF occur. And again, just so that you are comfortable with this, let me just mention that the way to be done, and I will just leave the steps to you. The Rayleigh PDF is given by V by sigma squared e power minus V squared by 2 sigma squared, okay, for V greater than or equal to 0. The peak of the PDF basically says that I want to differentiate with respect to V, set it equal to 0, find out what is the condition that comes out to be. So, basically the point at which you get maximum PDF, V max squared is equal to sigma squared, or in other words, or the maximum value of the PDF is, which maybe we shouldn't call it V max, the place at which the maximum occurs, at maximum of PDF. Okay, so basically V is equal to sigma is where the peak of the PDF occurs, which is what you can see, where V by sigma is equal to 1. That means V is equal to sigma, you will see that the PDF will peak. Now, what happens at the value of the mean? At the mean, already the PDF is dropping. At the RMS value, it is further dropping. Again, it starts to give you some insight as you work with this more and more. So, please do make sure that you are comfortable with the shape where the peak occurs and what these values are. Another very, very important offshoot of the Rayleigh PDF is the cumulative distribution function. Now, here again, from a mathematical viewpoint, is given a PDF, I know how to compute CDF. Why do we labor over this one? But it turns out that there is a lot of useful information that we get from the CDF from an engineering perspective. So, therefore, we will spend a minute to highlight this. So, given the Rayleigh PDF, I wanted to compute the CDF. So, the Rayleigh CDF is the cumulative distribution function Fv of V. This is the probability that the random variable is less than or equal to some threshold value V. So, which means that cumulative distribution function, my variable goes from 0 to this value uppercase V. I have to integrate the variable. Just to avoid confusion, I am going to use U as my variable of integration. So the PDF integrated from 0 to V is the answer that we are looking for. Okay. So again, please do a change of variable. W is equal to U by sigma squared. Again, I'll assume you're very comfortable with these types of operations. This will give me the cumulative distribution function as 1 minus e power minus V squared by 2 sigma squared. Okay. And once you have the CDF, there are some interesting observations that we make from here, but let's take it one step at a time. The first one is the median value. The median value. When does your cumulative distribution function, cross the value of 0.5? So what is this value? That is, we call that as V50. That's your median value in your distribution. So you can substitute Fv of V to be equal to 0.5 and basically verify that V50 is given by sigma times square root of 2 times natural logarithm of 2 ln 2. Again, very simple manipulation. I'm assuming it is very straightforward for you to look at that. Okay. Now here comes another important observation, or again insights start to come from the equation once we take the following steps. We had mentioned earlier that Vrms squared is equal to 2 sigma squared, expected value of V squared. So and this also means that Vrms is equal to root 2 sigma. So the cumulative distribution function can actually be written very nicely in terms of the Vrms. 1 minus e power minus V by Vrms whole squared, minus Vrms the whole squared. Okay. Now, why is that an interesting form? We're going to see it in a minute. But basically, I hope the steps, we've skipped steps, but those are all simple ones that I'm sure you will be able to fill in. So the reason for this is the following example, where the question that is going to be posed to us is that what is the probability? What is the probability that the instantaneous received signal power, so that the received, again instantaneous is understood, it's a time varying, at a given time instant, the received signal power is 20 dB, is 20 dB lower than the mean power, mean signal power. Very valid question, because you told me that signal is fluctuating, and I want to ask the question, what is the probability, given that you have now understood what a PDF is, what the CDF is, all the different characterizations of the mean, the variance, the RMS. So first question, what is the mean received signal power proportional to? Expected value of V squared, because the signal is not changing, that is normalized. So the mean signal, received signal power is going to depend on expected value of V squared. Expected value of V squared, which is the same as Vrms whole squared. Okay, so that's the reference point. Now the question that is being asked is, what is the probability that the received signal power, the received signal power, instantaneous received signal power is proportional to V squared. So the question that is being asked is, what is the probability that V expressed in dB, what I mean by that is 20 log base 10 of V, that represents the mean received signal power. V is the instantaneous received signal power is less than or equal to Vrms expressed in dB minus 20. Am I correct? That's a question that is being asked. What is the probability that the instantaneous received signal power is less than the mean signal power by 20 dB? It's a very, very useful question. Now, if you want to see where this is leading to, if you go back and look at the signal fluctuations, the question that is being asked is, if this is VRMS, that is your mean received signal power, what is the probability that your signal exceeds a 20 dB margin? Basically, what is the probability that it goes below 20 dB with respect to the mean signal power? And that is what is the question that is being answered here. So basically, rewriting this, it would be 20 log of V by VRMS. This has to be, let's set it equal to minus 20. That basically tells us that V by VRMS is equal to 1 by 10, 10 power minus 1. So what is the probability that this condition is satisfied is the same as going back to the CDF function, because this is the condition where I substitute V by VRMS equal to 1 by 10. So this probability using the CDF can be given by 1 minus e power minus 1 by 100, which is approximately 0.01, well, let me write the exact value, you can approximate it, 0.00995. Okay. So it's approximately 1%. So it's a good tool for us to have. So why did I compute CDF? Because I'm always interested to find out what is the likelihood of my signal going below some thresholds. And the one that you would want to look at is not the PDF. You would want to look at the CDF, because any envelope which is less than this also is going to be a problem. So using the CDF is a threshold by which we ask the question, what is the probability that V is less than or equal to some threshold? Now we are talking about a threshold where V squared is less than the corresponding RMS value minus 20 dB. Okay? So I hope this example gives you an indication of the usefulness of the CDF. Any questions?
Probability of V square expressed in dB, right?
Same thing. Basically, V squared means you will take 10 log V squared, 10 log 10. That's why I've said I've taken it as 20 log.
The probability of V square.
V squared. I don't think it matters, because I've given you the expression that I'm using. Because if it is V expressed in dB, it has to be 20 log. That's the same as V squared expressed in dB, which will be 10 log 10. 10 log V. So both mean the same thing. If I didn't give you this expression, then there is a ambiguity. But given this expression, that's how we are writing V in dB. If it helps avoiding confusion, no problem. Let's write it as V squared. Okay. So basically, this is a good way for us to visualize the benefits of working with the CDF. Okay. Now, there is another very important element that comes out from the CDF, which I would like for us to highlight, and again work with that as we move forward. So the other element that we notice is that the cumulative distribution function, f V of V, is given by 1 minus e power minus V squared by 2 sigma squared. Or okay, this is the expression that is given to us. Now, for small values of V, then V squared by sigma squared also is small. So therefore, we can approximate this f V of V doing the series expansion of e power minus x, that this is approximately given by V squared by 2 sigma squared. Now, a good check for this approximation would be go back to because the previous case we were looking, this is the same as V by VRMS. V by VRMS whole squared, correct? And the V by VRMS that we got in the previous case was 1 by 10. Square it, 1 by 100, 0.01%. So again, it's a sanity check that this is a good approximation. What else does it tell you? It tells you that in the entire range where V is small, this approximation is going to hold, and if I plot it in dB, the CDF as a function of V by VRMS in dB, then what I will see is a linear line, because it is a square term. Slope is equal to 2. So basically this is the linear portion. The red graph shows you the CDF drawn on a dB scale, and you can see that the portion is very, very linear. Okay, now I would like to also introduce you to another very important aspect, and that is the notion of how do we work with this. Basically, I want to relate the fact that now we understand that the small scale fading is going to cause dips in the signal. How bad are those dips? We can look at the CDF and we are going to tell. Now the question is, previously we allocated some margin in my link budget for the shadowing. Now the question is, should I allocate margin for this fast fading or small scale effects of fading or not? What are the implications if I do not and if I do? So basically it is building on a understanding that we have already developed, but we want to take it to the next level. Okay, so let us look at an example which should give us some insight. So keep this picture in mind. This is the signal fluctuation. Now there is VRMS, that is your mean received signal power. Okay, you can draw a line and because of signal fluctuations, your x-axis is position. That means displacements with respect to some reference point which you call as 0, 0. You move in a certain direction, the signal is fluctuating. Okay, that's we'll come back to interpreting it in a minute. So basically that is my threshold level. Now if I do not have any additional margin, what is the probability that I will have outage? Let me say that I am at the edge of coverage with respect to path loss and shadowing. I am at the edge of coverage. Now fast fading occurs over and above that, but I have not allowed for any additional margin. What is the probability that I will have outage? So the question now becomes, what is the probability that the received signal V is less than or equal to VRMS? Correct? Because that's where I have received. If it goes anything below, because basically that is the threshold of my receiver sensitivity. If it goes anything below that, then I am in trouble. So this from the CDF tells us is 1 minus e power minus 1, because V by VRMS is equal to 1. This is 0.632. What is that? Bad situation. 63% of the time you are going to be in outage. So this is the same as 63.2% outage. And you say, my goodness, I can't tolerate that. Please tell me what's the margin I should put down. So now comes the interesting trade-off. How much margin should I put into the picture? Then you say, okay, what is the outage that you can tolerate? 1%? How much margin should I give if I want to have 1% outage? 20 dB, that's what we already calculated. Remember, the likelihood of you going below threshold of 20 dB is 1%. If you want your outage to be 1%, then what should be the margin that you should provide? 20 dB, because with respect to VRMS, 20 dB, if it goes, no problem, you will still survive, because that much margin you have provided. If it goes beyond that, if the fade goes beyond that, only then you will go into outage, and that is precisely what the calculations tell us. Okay. Now let us say that you say 20 dB, that's ridiculous. How can I add 20 dB margin over and above? I already added 10 dB for shadowing. That means this is a huge amount of cost that you're going. So okay, now let's look at trade-offs. Then you say, okay, give me 10 dB margin. Okay, what if I give only 10 dB margin? I cannot afford 20 dB margin. So the interpretation of that will be in the following form: 20 log V by VRMS. This is equal to minus 10. That's basically what you're saying is, if I have VRMS and I'm going to have a 10 dB margin. That means only time I will go into outage if V exceeds that, basically falls below that 20 dB margin, 10 dB margin. So this is the threshold that we have, which basically says that V by V RMS is equal to 1 by 3.16, which is approximately 0.316, and the probability of this happening. So probability that, okay, we'll write it as V squared to avoid confusion, is less than or equal to V squared. This is all in dB. This is V RMS in dB minus 10 dB. Okay. This one is given by 1 minus e power minus 0.316 squared, 0.316 squared, which is approximately 0.095, which is approximately 1%, 10%. Okay? Good. We have accomplished something very significant in today's lecture in understanding what is the price that we have to pay to build a system that is robust in Rayleigh fading. What is the secret? Margin. Margin is, now this one says with 10 dB, I am likely to have 10% outage. No problem. We are going to live with that, but now the engineering intuition starts to kick in. So I have 10 dB fading margin, shadowing margin. Now I have 10 dB for the fast fading. Two together I have 20 dB margin. So if I don't have the effects of fast fading, I can use 20 dB for shadowing, or if I don't have shadowing, I have 20 dB for fast fading. So basically you are trading off between shadowing and fading, hoping that you're not unlucky and you get hit by both at the same time. So now comes a very interesting question. What is our x-axis? X-axis is position. So that means the faster I move, the more fades I'm going to encounter. Is that correct? That's fair enough, because the faster I move. If I'm going to move slowly, then my signal is going to slowly go, it will still be good, then it goes to bad. When it goes into bad, it's a problem because it's bad for quite some time, and then it comes out into good situation. Whereas if you're moving fast, good, bad, good, bad, it's basically shuffling very fast between good and bad. Which is better? Which is better? Fast is better. Okay? Everybody would agree fast is better because you don't get stuck in a bad situation. Because what would happen if you sat in a bad situation and it says bad, call drop, gone. Because why? Because speech coder cannot survive beyond a certain point, and beyond you've already allowed for 10 dB margin, and this has gone below the 10 dB margin, and therefore you're killed. So the good news, the thing is fast, move fast. Don't walk slowly, move fast. But you can't control the user behavior. If they want to walk, they'll stand in one place. The problem comes when your user stands in this place and starts talking, because then he's not moving, therefore the call is going to drop. You know the secret behind that.
If we move fast, then many number of times calculation needs to be done.
Okay, that's a good observation, because what we said was that in order for us to track or to do coherent detection of the received signal, you must estimate. I'll just rephrase that. He said you have to calculate very often. What is it that you're calculating? You're calculating the phase, because this is not only an amplitude, there's also a phase associated with the fading. You have to constantly keep computing the phase so that you can coherently detect your signal. Otherwise, what will happen? Your phase reference will be wrong. Your BER will once again get affected, and therefore, so fast is not necessarily good from a receiver point of view. It actually adds complexity to your receiver. So the key question is, well, okay, one point of view says, go for high mobility. That's a good thing to do. Yes, it's good because the probability of outage decreases, correct? That's the reason why we would like this. On the other hand, low mobility, probability of outage will go up. So what if, and just so that you know the statistic, about 80% of India's mobile traffic comes from pedestrian users, which means that they are not moving very fast. 80% of our traffic. So then what do you tell those 80% of Indian subscribers? Too bad, you're sitting in a bad spot, call drop, I can't do anything about it. what do? You have to solve the problem. 80% of your traffic is, moving very slowly, not moving fast. Once they go into a bad situation, it will take some time for them to come out of it. FEC. When you say, oh yeah, good, because FEC is good because it will protect you against some number of errors. It turns out that even FEC will run out of correction capability if you start giving whole a series of frames that are in error. So FEC to some extent will protect you, but will not bail you out. You need something else. What else? You've already studied that. Handoff may be okay, but you may be close to the base station. You may not be in a situation where you really need a handoff. Let me go back to this graph. That's why I thought, as I mentioned, these pictures all have a purpose. Okay? Now, this carrier frequency and this carrier frequency are related. They are shifted by Doppler, but they have a basic underlying carrier frequency FC. This pattern that you have seen here, in some sense, depends on FC. Right? Because the peaks and troughs are going to be. So this depends on FC. If I want to disturb this pattern, what should I do? Frequency hopping. Just change your frequency, because then what happens? This pattern gets shifted. Then even in the same location where you are, now it may be a better frequency in terms of multipath fading. So FEC is good, but frequency hopping is better. So we just make an observation that we will use a combination of FEC to protect you against some number of fades, plus frequency hopping is probably a very good mechanism for us to take care of the multipath fading. Okay? So again, hope that you are starting to see the benefits of this type of understanding. Okay? So let me give you one exercise, as always, something for you to try out. This is an exercise. Find out what is the probability of outage. What is the probability of outage if I have 15 dB margin, power margin? That is, I have 15 dB margin for fast fading. So if this is the margin, what is the, obviously it should be somewhere between 1% and 10%. Please verify that this comes out to be something very close to 3%. Okay? And again, you can see that the CDF has played a good role for us to understand the various elements of what we want to study in terms of the effects of fast fading. Okay, now comes a very, very important part of the lecture. I hope this graph is very familiar to all of you. Computer assignment number 1, you drew the theoretical graph. Q is Q function of square root of 2EB by N naught. BER is Q function of square root of 2EB by N naught. Correct? Okay. Now, basically, let us say that you are operating somewhere close to 10 dB, you have 10 power minus 3 BR, you're very, very happy. Now, you change it from an AWGN channel to a fading channel. So, the SNR in a fading channel is given by mod Z squared times the EB by N naught that you will have in a AWGN channel. So, this is the SNR in an AWGN channel. We had already introduced how we are saying that. Now, mod Z, we also have used the notation alpha in our expression. So, mod Z or alpha is the same. So, this is the same as alpha squared EB by N naught. Okay? Now, if I told you, without telling you anything about whether it was fading or AWGN, I told you that my SNR is alpha squared EB by N naught, asked you to compute the BER, you will basically say, now where is this alpha squared EB by N naught? Let us say it is somewhere here. So, this corresponds to alpha 1. Alpha 1 squared EB by N naught is somewhere between 7 and 8 dB. You will look at this graph and you will tell me, okay, it's close to 10 power minus 2. Not bad, but it is. Now, what if, so alpha 1 is specified. I give you an alpha 2, which is horrible. Somewhere between, it takes the SNR to 2.5 dB. So, now it has gone close to 10% of errors. then another scenario where it actually got better than 10 dB. It is around 11 dB, it's 10 power minus 4. So, oh, that's really good, because this is what fading is doing to you. Sometimes it gives you an SNR that is bad, sometimes it gives you an SNR that is good. And then you have to average all of them, because it's the average of over all the SNRs that you will encounter. Now, if you look at the averaging process, which are the events that dominate your bit error rate, resultant bit error rate? It is not the 10 power minus 4, because 10 power minus 4 does not add much errors. What adds is this is going to cause a big problem, this is going to cause a big problem, because these are. So, the resultant BER in a fading environment, the average SNR threshold is actually here. It's just that from AWGN I moved to a fading environment, and then you ask me to look at the BER. This is AWGN BER. The BER in fading is this. BER in a fading environment, it is much, much worse. It does not even, it takes a long time to even hit 10 power minus 2. So, which means that I actually am working in a very, very error prone environment, and therefore I have to pull out all the techniques that I know in digital communications, FEC, equalization, all of the elements that I know, because this is going to be a huge challenge for me to solve. Okay? So, the theoretical expressions, I will write it down and then conclude today's discussion. Probability of error of BPSK. This is performance in AWGN channel. This would be given by Q of square root of 2 EB by N naught. Now, the same thing in fading environment. Probability of error in BPSK in fading. Immediately you should ask, what is the value of alpha? Given a particular value of alpha that is introduced by the fading, this would be given by Q of square root of alpha squared 2 EB by N naught. In most cases alpha is going to be less than 1, and therefore the bit error rate is now a function. So, BER in fading is actually a function of the EB by N naught. Yes, that is your nominal value where you have set. It is a function of that. It is also a function of the instantaneous value alpha. So, if I were to ask you what is the probability of error of BPSK in fading, what would you have to do? You would have to take the integral of Q of square root alpha squared EB by N naught times the probability distribution of alpha, the alpha, and alpha will go from 0 to infinity. This would be your fading environment, and this is the graph that we showed was really bad. Okay? How do we get more intuition about this type of system? How do we deal with this kind of a system? Those are things that we will build on in the lectures to come. Okay? Let me stop here. Thank you.